Welcome everybody. Hopefully you had a good vacation. Vacation's over now though. This is Civil Engineering 331, Hydraulic Engineering. And this is a continuation of what we did in fluid mechanics, and it focuses a lot more on application and problem solving. And we have a pretty sophisticated and intensive design assignment in this course. And so it's kind of the culmination of the class is we'll go through and do some design. A few announcements to begin. First of all, the textbook details are here on the syllabus. I'm going to give you that here in a minute. So I encourage you to purchase the textbook. Some of our homework problems this semester will come from the textbook. And the textbook does a really uniquely good job at explaining difficult concepts. I've run through, over the years, a lot of different textbooks, trying to find one that kind of broke down these concepts into the most simple terms and using the most plain language. And so I think that it's worth getting. I'm going to give you the syllabus today. And then on Wednesday, I'll give you the overall schedule summary that shows which topics are going to be addressed on what days and when various homework assignments are due. And I also hope to have the lecture notes available for you, posted online by Wednesday. So we're going to get into the material today, starting in Chapter 7 of the book. The way that this book is set up is it could maybe be used as a text for fluid mechanics, the first 6 chapters. But then the hydraulic engineering stuff starts in Chapter 7. So that's why we kind of skip straight into Chapter 7, is beginning with topics related to flow resistance. Okay, so first of all, let me hand out the syllabus, and we'll spend a few moments going over that. All right. So you can see the course description there and meeting times. Obviously you know that if you're here right now. My contact details are provided along with the office hours, or Monday, Wednesday, Friday from 11 to 12 and 2 to 3. And I would just love to have you stop by my office when you need help. Of course, I'll do my best to answer your questions via email, but the advantage of us meeting face-to-face when you've got a question is that I can offer, I can tailor my answer by asking a couple of follow-up questions, looking at what you've done so far. So, you know, if you're not on campus, you can also call me on Teams. And there's a link that I'm going to be putting onto Blackboard where you click it and it'll immediately call me on Teams if you've got it installed on your phone or on your computer. And that's also a good way for me to help you, because you can do a screen share. And for example, if you're working on a spreadsheet, I could actually see your spreadsheet function. You can show it to me. We can find the problem together. So that's just a quick word about, you know, it's best to have our interactions be live if you're asking for help. But if you do email me, please give me as much information as you can, and I'll do my best to help you with that. So the COVID-19 related stuff, each of you should have already filled out the vaccine registry and the return to campus agreement. And if you don't have those signed, they're going to start dropping people from classes in the next day or two. So it's really critical that you just jump through the hoops and do that. The information is provided here in the handout. The details for the textbook, including the ISBN, is provided there. Does anybody already have the book? Anybody purchased it yet? How much did it cost for you? Did you get it from the bookstore here on campus, or did you get it someplace else?
Amazon, I think.
Amazon? Typically, Amazon has it available for a rent for really low. It varies from semester to semester. Sometimes it's as low as $20. Sometimes it's a bit more than that. So below the textbook, it mentions that this semester you're going to be using design software for the project that doesn't have a Mac version. So the design software was only working on Windows computers, and so you're expected to track down a Windows computer that you can install and use that design software on. And there's going to be some days where I'll ask you to bring your computer into class so that we can solve examples together. And typically that will be Microsoft Excel. The design software we may use a couple of times in class, but more you'll be doing the design work on your own. The course is going to be on Blackboard, and they've made some changes to Blackboard in between semesters for some reason. And it's going to take me a while to figure that out, maybe you as well. But if you have any questions, the IT service desk can help out. I'm sure I'll be getting in touch with them as well. You can see the outcomes and the course purpose are described, and we're going to get into that here in a minute, so I won't repeat it as we go over the syllabus. But what I did want to point out is that new this semester, I'm going to start awarding points for attendance. 10% of your course grade is determined by attendance. And so each unexcused absence you have during the semester would reduce that by 1%. And so you can just think of it as a free 10% as long as you just come to class each time. So here in the grading scale, you can see that 18% of the course grade is determined by assignments, 18% by midterm 1, 2, final, project, all of those are 18. And then the attendance fraction is 10%. I'll drop the lowest one homework assignment of the semester. And of course, my late work policy is that I don't accept late work unless there's a university excused absence. So any questions so far on the syllabus or the course policies? Okay. The rest of it, I guess, I would just ask you to read through on your own time and pay special attention to the academic integrity section, because, I mean, the rest of it is pretty standard university policies, but the academic integrity language is something that I developed just to communicate my expectation that when you turn in something for points, something to be graded, I expect that you're the one who did the work. And so it would be against that to find a solution online and copy that. Or it would be against the course policies if you sat down next to another student and you just copied their assignment. Or if you were working with another student and they were the ones who were actually doing the thinking and the calculations and you were just kind of copying what they did, you didn't really do the mental lifting on the assignment. So my expectation is that anytime you submit work to me, it's stuff that you solved. And it's okay for you to talk about the problems with another student, and it's okay for you both to help each other out, finding mistakes or checking for errors. It's okay to compare your final answers. That's all fine, but the work should be yours. All right, so the last thing on here says course schedule, and I'm going to give you the course schedule on Wednesday. I just want to think through a little bit about a couple of the assignments and what their due dates are going to be. So I'm not quite ready to give you that yet. If you do have any follow-up questions on the syllabus, then please just let me know. Okay, hydraulic engineering is pretty fascinating, I think. Here's a photo of a bridge in Germany, the Magdeburg Bridge. And what you can see is that it's water is being carried by a bridge over a river. And so this is a canal, which is used for shipping goods between two industrial towns in Germany. And this is the Elbe River, which the barges used to go down this channel, but it was kind of a circuitous route. They had to zigzag around, and they wanted to go more directly from point A to point B. So they built this, first of all, a levee system. You can see that the water is above the elevation of the surrounding land. Usually, a river is lower than the surrounding land. But here, they had to have a levee to raise the water level up. So this gives you kind of an overview that the Elbe River connects these two different industrial towns. And in the past, the barge would have to go along a short canal, get into Elbe River, go downstream, and then take a more lengthy canal to get back to this second industrial town. But now the two are connected more directly, and it seems like $500 million, that's a lot of money, but not that much when you think about what they've accomplished here. Just the bridge alone, it seems like you could spend $500 million on that. But it's not just the Germans who have pretty interesting waterway solutions. There's a water wheel in Scotland. This is used to lift boats up from a lower reservoir up to a higher canal system. And so it rotates. I think you could probably get that sense by seeing the big spoked wheel here. And so usually what will happen is there is water in the canal here, and a boat would go to the end. They would seal one end of it, they'd rotate it down, and then this door would open up and the boat could go out. And at the same time, there could have been a boat on the lower end that's being lifted up to the elevated canal. So it's kind of an ingenious way of moving water traffic upstream and downstream. And of course, we have a pretty sophisticated waterway system here in the United States, the most important inland waterway network in the entire world. The Ohio River, which connects to the Mississippi River and dumps into the Gulf of Mexico, allows the most fertile agricultural area in the world, the Midwest, where people grow soybean, corn, wheat. The agricultural products of the Midwest go all over the world, and one of the things that makes it so efficient is the fact that those heavy agricultural products can be shipped for very, very low cost on barges up and down river. It would add tremendous cost if all of that, all those grains had to be taken by truck, or even rail car isn't as efficient as barge. So this is just a look at the river traffic starting at Pittsburgh, and you can see the different Army Corps of Engineers districts and which locks and dams they have primary responsibility for. I think that we here in Huntington are in the Greenup Pool. So you can see Huntington on the map. That's a little bit downstream, closer to Ashland, where the next lock and dam is. But if you go upstream, like if you drive up Route 2 far enough, you'll come to the Robert C. Byrd Locks and Dam. So there's just a series of all these different locks and dams working its way all the way from New Orleans up to Pittsburgh and beyond. So it's fascinating. This course includes both open channel flow, which is what we've just been looking at. We've been looking at, the water bridge and the water wheel. That's considered open channel flow, but it also has closed conduit flow. So there's both water flowing through pipes and water that's going through open channels that's not pressurized. And there's very different equations and very different design methods we have to use for those two different situations. And so we're going to start the semester by talking about closed conduit flow through pipes, and then later in the semester we'll transition over to open channel flow. But in both cases, we're wanting to know about the amount of water, the timing of when it arrives, how much it has to be delivered. So the purpose of a closed conduit system, like a municipal pipe network, we're trying to deliver water to consumers. And so you have to do a little bit of an investigation to find out how much water is going to be used at a house. Not just over the course of a day, but how much water is going to be used all at once, like at the peak point. So think about in the evening, when you're washing dishes, maybe your little brother is taking a shower, Your parents may be watering the lawn. The dishwasher is running at the same time that the clothes washer is running. And maybe the water softener is going through a cycle of recharging the ion exchanger. So there could be a lot of different things that are happening simultaneously. And so part of what engineers do is they estimate the amount of demand that there's going to be, and they pool it all together for a residential area, and then a series of different neighborhoods. You'd analyze the water demand, and all of that is going to be significant to figure out how big does the pipe have to be. Because that's ultimately what the hydraulic engineer is sizing when you are doing closed conduit flow, is the size of the pipe that's required. And you'd maybe just say, well, why not make it just a really big pipe? Because then it doesn't matter if there's a lot of flow or a little flow, you're always going to get enough pressure downstream. And of course, a large pipe would be expensive because there's a lot of material there. It would be more costly to install because the fittings would be more difficult and there'd have to be more trenching. So it's a balancing act of providing enough pressure downstream, making sure that the pipe is large enough, but not spending too much money. So it's a balancing act, and that's what you're going to do in your design project, is that iterative process of trying to make the pipes as small as possible, but still providing enough pressure downstream. So we'll consider water that's flowing through pipes, and most of the time water's flowing through a pipe, it's pressurized. But there's also situations where water is flowing just by gravity in a pipe, meaning that the water isn't full. The water is flowing through a pipe, and the pipe is just a channel. So think about sewer systems. Sewer systems aren't pressurized, and most of the time, the water is just filling part of the pipe's capacity. So sewer systems and stormwater drainage pipes, like they call it a storm sewer, that's also gravity flow. We will do some analysis of sizing for channels and figuring out how big reservoirs should be. So we'll be busy this semester. And the interesting thing about hydraulic engineering is it's not just about the calculations, because water is an important resource. There are a lot of legal issues, there are a lot of political and economic topics, and even social issues that come up when you talk about the allocation of water. Just recently, I was invited to join a group of people who are meeting to discuss a water dispute in Eastern Africa, where I'm sure everybody here's heard of the Nile River before, but the Nile River is experiencing more dispute than ever before because there's a very large hydropower and dam that's being built on the Nile River. And the Nile River, most people think about it in terms of Egypt, but also it flows beyond Egypt up into Ethiopia and beyond. And so there are a lot of places in the world, including the United States, where water flows across state boundaries and even international boundaries. And it's a resource that people want, and figuring out who gets it is sometimes a sticky subject. So it's not just all about the calculations when it comes to the considerations of water design. So this is a picture that I took when I was working on my PhD in Indiana. I went to Purdue University when I was getting my doctorate degree. And this was in the basement of a water treatment facility. And I spent hours and hours in this basement taking measurements of water that was taken from, this was downstream of a sand filter. So they were taking river water and going through a series of steps to make it so that it was pure enough for people to drink. So you think about how dirty river water is, it's pretty gross. You've got to do a lot of stuff to get it so that it's safe to drink. And so I was, in my PhD, doing some work related to ultraviolet disinfection of drinking water. So instead of using chlorine, another way to kill bugs in water is by shining a bright UV light on viruses, bacteria, protozoan pathogens, cryptosporidium. and the UV will inactivate them so that they can't cause a disease in you. So I was doing a project related to that, and this is a picture of, just to give you a sense of how complicated it is, just it's called a pipe gallery, where the water's flowing in and out of these different filters at different locations, depending on how many of them are being filled or emptied at any given time. So this is closed conduit flow. Here's an illustration of open channel flow. This is a picture that I took when I was living in the United Arab Emirates, which is a desert. And you might expect water issues wouldn't be that significant in a desert. But even in a place like the UAE, where it only rains 4 inches per year, water issues are really important. You can see that they have steep mountains there. There's no vegetation growing on the mountains. And so when it rains, the water falls onto this rocky mountain and moves very quickly towards the low points. Here in West Virginia, we call, you know what a holler is, right? Out west, they call it a canyon if it's really big. Here it's a holler. In the UAE, it's called a wadi. And so flash floods from wadis like this can be really dangerous, and there's huge amounts of water. So this is a very large open channel, and somebody had to figure out how big should this trapezoidal channel be. It's taking the water out to the ocean. This is discharging into the Indian Ocean, because this was on the UAE has one side of it is bordering the Arabian Gulf, the other side is the Indian Ocean. So this is the part that the water just goes into the sea, and so figuring out how wide to make that channel is a calculation that they had to combine hydrology, which is studying the rainfall patterns and the earth characteristics, but then also the hydraulics. How much water can be conveyed in an open channel like this if you're making it smooth concrete, if you know the slope, what's the flow rate that can be carried by a channel. So these two pictures illustrate the closed conduit flow, trying to figure out how big should a pump be, for example. When you've got a certain elevation that you have to lift the water from the basement up to the next phase in the treatment process, which was a clarifier. So how big should the pump be in order to lift the water and to overcome the effects of pipe friction? It's a hydraulic engineering calculation. This open channel is part of the course that we're going to be going through, trying to figure out how large a channel would need to be to convey a certain amount of flow. To a lesser extent, we'll spend a little bit of time talking about reservoirs in this course. This is a photo from Northern California, where they use reservoirs where they can in order to provide a little bit of a buffer for agricultural use of water. The Central Valley of California is where a large portion of America's fruits and vegetables are grown, in the Central Valley. Almonds, lettuce, onions, garlic, rice, all sorts of stuff is grown in California and shipped out to us. Chances are that, if you buy lettuce at the store, it was either grown in the Central Valley of California or occasionally in Arizona. But most of the time, the water that's used to grow those things is runoff from snowmelt. So the water is trapped in snow. In the spring it begins to melt, and then they contain it in reservoirs before they take it down into the growing areas. So we'll talk a little bit about reservoirs this semester as well. This is a sneak preview of a map that you'll become very well acquainted with when we do the design project. Because in the design project, you're going to go through the process of looking at an area that's going to be developed and doing a demand analysis to figure out, based on a certain number of people in that area and knowing a little bit about how much water they'll be using on a per person basis, you'll try to size the pipes to figure out what's the most efficient route for the pipes to take, and also how big do the pipes need to be in order to deliver a certain amount of pressure. What do you suppose these curved lines are?
Contour lines.
Elevation contour lines, that's right. And so that's another thing that you'll be taking into account is how does the water pressure change as the water is moving downhill? It's not just a flat area, but you've got both the effective pipe friction that you're having to account for, but then also changes in elevation. So I'm excited for you to go through that the project, because I think you'll learn a lot, both of the engineering design process, but also some specific software tools that will be useful and that you can put on your resume. Okay, so let's get into this technical material that is in chapter 7 of the textbook, flow resistance. This is, if you remember back to fluid mechanics, in fluid mechanics we were using that book by Clayton Crowe, and chapter 7 of that book was called energy. We learned about, for instance, Manning's equation and the Hazen-Williams equation in fluid mechanics. And just very briefly, I told you about the Darcy-Weisbach equation. It's more accurate than either the Manning's equation or the Hazen-Williams equation. But just to step back a little bit and talk about the fundamentals, when water flows either through a pipe, or if water is flowing, like this picture is showing, where water is going around a dam. So it's the bypass for a dam. This is where fish would be able to migrate upstream around a dam. And the color codings is just illustrating different velocities. So where it's blue, the water is moving more slowly. The cool colors mean slow moving flow. And where the colors are more warm, like the red and yellow, represents faster moving flow. So this is an open channel, and what this shows is that the water velocity is higher in the center of the channel than at the edges. And so any speculation on why that is, it's just flowing by gravity. It's not like there's pumps that are forcing the water in any particular location. But for an open channel, why would the flow velocity be greater in the middle?
Friction.
Okay, friction, what do you mean?
Friction from the sides of the channel.
Okay, good, that's right. So it's this effect of when it's near the edge of the channel, it's experiencing some resistance to flow. We talked about the no-slip condition in fluid mechanics and how water that is in contact with a stationary surface will have the same velocity as that surface right at the edge, where the two are coming together at the boundary layer. But then the further away you get from that boundary, water is able to slip over itself, and so the highest velocities will be at the center. And the same thing is true in the pipe. This is just an illustration of water flowing through a pipe, where you can see at the edges the velocities are less, noted by the darker shades, and it's lighter shades in the middle. And it's turbulent flow. This is not laminar conditions. This is turbulent, where there's a lot of cross-current flows and swirls and eddies and turbulence, but there's more turbulence at the edge and less of a forward velocity because of that. So viscosity affects the resistance to flow, fluid viscosity, and so if you're trying to force pancake syrup through a pipe, you're going to need more pressure to do that than water, because pancake syrup has a higher viscosity. It also depends on the flow conditions, the resistance. So the higher the velocity is, the resistance to flow increases, and it's not linear either. That's one of the things about Darcy-Weisbach equation that's valuable, is that it accounts for the nonlinearity in the relationship between resistance and flow velocity. How deep the water is going to affect the flow conditions, where if you have water that's flowing over a concrete surface and it's very shallow, the water velocity will be slow. But the deeper the water gets, the top layer of water is further away from the bottom where the concrete is, and there's more resistance. So all of these factors need to be accounted for in order for us to accurately model the effective flow resistance, and the shape of the channel as well. Of course, laminar flow can be described as when the Reynolds number is less than 2,000, and just to refresh, Reynolds number is velocity times diameter divided by kinematic viscosity. And so when you have laminar conditions, the flow is different than turbulent. And I'm going to show you a diagram in just a minute, and there's a special curve on that diagram for laminar flow. And you won't use the laminar flow curve very often, simply because it's very uncommon to see a Reynolds number less than 2,000. Okay, so here's that Moody diagram. Let me hand out the Moody diagram to you, because we're going to work an example. Just, that's strange, I don't recognize that at all. This, okay. Now you can see here on the bottom left is the Darcy-Weisbach equation. The Darcy-Weisbach equation is a way of predicting how much head loss there's going to be due to pipe friction. What this Moody diagram is for is finding F. F is the unknown, the friction factor. All the other terms in the Darcy-Weisbach equation are physical constants, like the length of the pipe, the diameter of the pipe, gravitational acceleration, the velocity of the flow. But F is characterizing the resistance to flow. So this friction factor F. Now, if you have laminar conditions, if the Reynolds number is less than 2,000, it's really easy to calculate F, because it's just 64 divided by the Reynolds number. But it's not going to be that very often. Most of the time you're going to have to use the Moody diagram. And the way that the Moody diagram works is, I'm going to write this on the board because you're going to do it in just a minute. So step one is find the relative roughness, which is epsilon divided by d. And by the way, this is note K sub s equals epsilon. K sub s and epsilon, that just means the relative roughness of the material. So it is, if you had to represent the roughness of that surface as a spherical diameter particle, what would be the diameter of that particle? So step one is find the relative roughness, and then you'll look on the diagram on the right axis. You'll follow it over to intercept the Reynolds number. So find the Reynolds number. And so where the two join together, the relative roughness curve and the Reynolds number, is then you use intercept to find F. Okay, so the example that you're going to work, you can see it on the handout I've given you. Water flows 30 meters per minute through a 0.25 meter diameter pipe where the K sub s is 0.26. Okay, so with this given data, we know we have enough information through the data that's given to find the relative roughness, because you know the pipe diameter, you know the numerator in the relative roughness, this equivalent sand roughness as it's called, K sub s, also known as epsilon. Note that the units are different, so you're going to have to convert the pipe diameter that's given into millimeters, or the equivalent sand roughness, convert that from millimeters into meters. So start, find the relative roughness, and then once you have it, you follow the curve until it intersects the Reynolds number. Okay, so I'm going to pause for a second and give you a time to do the calculations, and feel free to write on this paper that I've given you. It makes it a lot easier to find what the friction factor should be if you go ahead and write on the paper itself. All right, so we have water flowing through a pipe that is 0.25 meters diameter, and based on its material properties, for 0.26, I think that's the equivalent sand roughness for cast iron. So, you know, we would have been told what this pipe material was, and we would go to a table to find K sub s. So, based on how rough it is relative to the opening diameter of the pipe, So these calculations, okay, so the relative roughness is 0.00104. And then for the velocity that's given, it's traveling 30 meters in a minute. That means that the velocity is 0.5 meters per second. And if that is the velocity, we're going to put it into the Reynolds number equation, multiply it by the diameter, divide by water's kinematic viscosity. Water is 1 times 10 to the minus 6 meters squared per second. So 1.25 times 10 to the 5th. What are the units of that, by the way? Reynolds number is unitless. All the units cancel out. So it's a dimensionless property. But now, with these two things, with the Reynolds number and the relative roughness, we'll be able to find out the friction factor. So the way that we do that is you follow the curve for the relative roughness, and if it was like, for example, 0.0015, we just go in the middle and stay between those two lines. So you'd use it like kind of like bumpers, a guideline, if you were between the two. But in our case, we're almost exactly right on top of one of those lines. So we follow the curve, and we're looking for the point of intersection. If you're not used to logarithmic axes like this, it can be a little tricky to interpret it. Sometimes people would go to the left instead of to the right. So it's showing 1.25 times 10 to the 5th. So like this would be 2 times 10 to the 5th, 3 times 10 to the 5th. So 1.25 would be halfway between 1 and 1.5. Maybe it would be a little bit to the right of that because it's the way that these longitudinal scales go. But what you can see is that the point of intersection, these two curves come together at a point, and then you follow that to the left, and so the friction factor is 0.022. So that's the final answer. That's the F value from the Moody diagram. We're going to use other ways of calculating the friction factor, because sometimes if you're doing like a multi-step calculation, you have to iterate, and you wouldn't want to have to manually go back to a diagram and like use your pencil and ruler. There are formulas you can use to estimate the F value, and that's what we'll pick up on for Wednesday. Any questions about this example? Okay, so this semester